This lecture will mainly focus on going through a couple of estimation method, and then I will walk you through least square method using the example of one of the questions I had for the exam, so you have an idea of how I can actually formulate problems, and then you have to use the method we have learned during the module. This lecture introduces the role of estimation in fencing, and then at the end of the lecture, every student should be able to understand the concept of least square estimation and maximum likelihood estimation and know how to apply them. So here we assume, let's take a very straightforward example. Let's say we have the country UK, United Kingdom, and then in UK we know everyone, or let's say the age of each one in the UK. And this one, because we know the entire population, we also know the true, let's say, mean value or the variance, or just the parameter of the population. But then we might want to take a sample that is much smaller, and then we need to estimate one parameter. It could be mu, it could be theta, knowing that the true parameters are known, but then can we have estimate of those parameters using a small sample size? So the goal is to estimate those parameters optimally based on a finite number of samples. That's the goal. So if we assume, let big Y, 1 up to big 1K, be K independent and identically distributed samples of a random variable, and the probability density function depend on an unknown parameter theta. So if we knew the entire population, of course, we could have known theta as well. But after our experiment, we only have a small sample. In that small sample, theta is unknown, and then we need now to try to estimate that based on the values of Y. So if big ones are random variables, we can then assume that small y are corresponding values of big Y. Random variables are given as capital letters, while values of random variables are given as small letters. So what if we define a function of those random variable? That function is used to estimate theta. We will then call theta x, which is then coming from our function, the estimator, of theta. But the values that theta hat will assume will then be the estimate of theta. So values of theta hat are estimate, and then we can take the estimate based on the small y. That means the values that we have actually measured. And this unknown variable may be random or non-random. And then you can use Bayes estimation theory for random parameters, maximum likelihood estimation for non-random variable, and so on. If we take now the maximum likelihood estimation, for that one, we need to define the density function. And if we let f of y given theta, so you want the distribution, the conditional density function of the random variable given theta. This is the conditional density function of y. Per definition, the likelihood function is given as L of theta, which is then the density function of each given theta. And of course, these are evaluated at different values given theta, which is, of course, the one we had before. As also we see in the video, this function is defined as the product up to k or n of each single random variable. So k and then k theta. Because they are independent, the joint distribution function of two independent random variables can be written as the product of both density functions. So if we find theta hat that maximizes the likelihood function, this is called the maximum likelihood estimator of theta. So it's a matter of maximizing the likelihood function, the L. And how do we maximize it? It can be shown that the derivative according to theta of the log of our conditional distribution function will allow us to obtain the maximum likelihood estimate of our problem. This is in short how maximum likelihood estimation works. But when we have an estimate or estimator, how do we assess if the estimator is good? So we do have some criteria. We talk about unbiased. unbiased estimator. So theta hat is an unbiased estimator of theta when, if the expected value of theta hat is equal to theta. The expected value is the weighted sum of all the values of a random variable. That also can be said as the expected value of the random variable is actually the true value. So how do we define the bias of an estimator? In case the expected value of theta hat is equal to theta plus some bias of theta, so the expected value is not exactly theta, but you have theta plus something. So if P of theta does not depend on theta, we could say P theta is a B, which is just a constant, that we say that theta hat has a known bias. That means if you take theta hat minus B, you can make it an unbiased estimate. A very simple example. You have your measurement being done here, and then you have some input U, and you are taking some measurement. In real life, your U is probably here, but your measurement has an offset. This is the output, and this is the input. So if we can determine that offset, it's just a matter of taking your output minus the offset so that you can get close to the input value. In that case, the offset works as a known bias. The same way, if the bias depends on theta, that we speak about an unknown bias. Remember that an unbiased estimator does not necessarily mean that this one is good. We also require, on top of being unbiased, that the variance of the estimator is as small as possible. So we should add another criteria of small variance. And the variance is the order central moment of a random variable. So therefore, we say that theta hat is a minimum variance and unbiased estimator if for all estimates theta prime, we do have the expected value of theta prime equal to theta, and we have the variance of theta hat, which should be less than the variance of each of them. One of the exercises today in Matlab will be for you to generate random numbers, and then look at the mean value and the variance of that random number. I'm going to see how different, when you generate enough numbers, you see how we can actually reduce, or the variance will tend to go toward the true value. Besides the unbiased estimator, we also talk about consistency of the estimator. This is defined as consistent when the limit of the expected value of theta hat approaches theta when the number of samples increases. That's what we're going to see today during the exercise. The same time where the limit of the variance theta hat goes to 0 when k increases. Let's take one example to make things a bit more clear. We all know that when you are asked to compute the mean value of a sample, we usually say the mean 1 over n, and then we sum over all the samples n. That's how we compute the mean value. And all of you know how to do that. That means we are actually here saying that we have an estimator in terms of one variable, which is given as the sum of all the input divided by the number of samples. The question is this biased or not? So that's what we use every day. And is this estimator biased or unbiased? So the bias can be given as the expected value of our estimator minus the true value. And then if there's no bias, of course, this value should be equal to 0. We already know that the true mean is equal to mu, and this is equal to the expected value of all x. If we then use b here, and then we compute the expected value of our estimator, this will be the expected value of 1 over n, summing over all elements xn. The sum and n is constant. It can be brought outside the expected value operator, and then we can easily swap between the sum and the expected operator. That means we can write it down as n minus 1, the expected value of x n. So this means we have 1 over n, and then sum. We already know that this one here, if you call it a, here is the same as here. So the expected value of xn equal to mu, and summing this will give us 1 over n times n mu, which is equal to mu. So the expected value of our estimator is equal to mu, and therefore, when we take the bias, which will be mu minus mu, the bias equal to 0. So the sample mean is actually an unbiased estimator of the true mean. For those who have not watched the video on least square estimation, I will give you the opportunity to do it now, and then we can run an exercise taking step by step how to solve those kind of problems. Last year, I had this question here for the exam. You have designed a perfect torque sensor with a linear input-output relation that can be described by the calibration line y equal to mx plus c, where x is the applied torque and y is the output potential. After connecting the sensor with other components in your system, you decide to take 3 measurements, x and y. So you have input-output 1, m minus 1, 0. If you give a 0 input, then you still have an output which is c plus 1. And if you give an input of 0.5, you have an output of the sensor, which is 0.5 times the slope. Then the question in the exam was calculate the sum of square error, considering your calibration line as the best fit. So that was the question for the exam. And of course, in the example, I will also take on a few more questions that was not in the exam, but so we have a good understanding. For example, we will also discuss if you can plot m for m equal to 1 and c equal to 1, if you can discuss if the calibration line is optimum, and then use the 3-point to compute the line using the least square error. So we have 3 points. First of all, we have the line that we assume is our perfect line. And then we do measurement. For the measurement, we got 3 points, 0, c plus 1, and then 0.5, 0.5, m. So if this is the measure data that we can actually say, let's call them y. And then if we use now the same input in our calibration, we should have got, if we say like if you use the model as an estimator, we should have got for x equal to 1, would have for x equal to 1, we should have, based on our model, we should have m plus c. For x equal to 0, our model should have given us c. And then for x equal to 0.5, our model should have been 0.5 m plus c. That's what we're supposed to get if we follow the calibration line. Now, what will be the sum of square error? The sum of square error is defined as the sum. You can divide by n as well if you want to, but here we just look at the difference between the estimated based on the model and then our measurement. That will be, if we take the sum of all, what we get is m plus c minus, or m minus 1 minus m plus c, which is m minus 1 minus m minus c square, plus c plus 1 minus c, c plus 1 minus c square, plus 0.5 m minus 0.5 m minus c squared. In this case, m is gone. We have only 1 minus c, minus 1 minus c squared, which is 1 plus 2c plus c squared. The second part, c is gone. We have only 1 squared, which is 1, plus here as well, this is gone, and then c squared, which will give us c squared, 2c squared plus 2c plus 1. So this is what we're supposed to get. Then, can we represent the line that is supposed to be our calibration line and then see how it relates to the point that we have measured? When m equal to 1 and c equal to 2, our calibration line should then be x plus 1 that we agree on. And we also have the 3 points that we measured. That was here. So when m equal to 1, we have 1, 0, 0, 2, and 0, 5, 0, 5. Huh? So we have 1, 0, a measurement, 0, 2, and then 0.5, 0.5 when we replace m equal to 1 and c equal to 1. Let's now plot our data. So our line is x plus 1. So let's start with the point first. For x equal to 1, y equal to 0, we have 1 point there. For x equal to 0, y equal to 2, 1 point there. And when they are both half, we have a point here. So those are the points that we have for measurement. Let's look at our line. The line is x plus 1, slope of 1, and intercept of 1. So we have for x equal to 0, y equal to 1. And then for y equal to 0, x equal to minus 1. Our line is going this way. So, what do you think about this line compared to the measured value? So one quick answer would be the line does not really fit the data. So either we have noted a wrong calibration line, or everything about the calibration of the system was wrong, or the way we are doing the measurement is completely wrong. If we assume that we trust our measurement, we were supposed to have a line that should be somewhere here that fits our data closely. Because if we use the least square error, what we want actually is to minimize the sum of square and then minimize the residuals, which is the distance between each point and the line. You can already see that in this direction here, we have large residuals using the calibration line as provided. So, can we verify if this line here is the correct one or this one is the best fitted? We can take a table. We have 3 points that we can say we have x, we have y, and then if we go back for the equation of the slope, we also have to have the product of xy, yi. We need the product of the mean value. We need the square of the input and also the square of the mean value. And the formula is given in the video as well as in your book. Just for recall, we are supposed to compute the slope as 1 over n sum of xy minus the product of the mean divided by 1 over n sum of x squared minus the mean of x squared. Our points are 1 and 0, 0 and 2, 0.5, 0.5. So the mean of x here will be 1 over 1.5 divided by 3. The mean will be 0.5. And the mean of our y will be 2.5 divided by 3. That should give us 0.083. We can also do the product. 1 times 0, 0, 0 times 2, 0, 0.5 times 0.5. This is 0.25. And for the product of the mean here, we just take this one and this one here. So we have 0.5 times 0.83. What we get is 0.415. This is the product of the mean. For the square of our xi, we have 1 squared, 1, 0 squared, 0, 0.5 squared, which is 0.25. And then the square of the mean would be here, which will be 0.25. So we are trying, based on the measurement, to find the line that best fits our data. So let's now compute the slope. The slope m will be what? We need now, and then this one here, 0 plus 0.5, this sum divided by n, which is the mean value of this one here, would be 0.83. So this number here is 0.083 minus the product of the mean values, which is here, 0.4115, divided by the mean value of x squared. The mean value of x squared will be 0.416. So we have 0.416 minus the mean of x squared, which is 0.25. That will be minus 0.332 divided by 0.166 equal to minus 2. So we see that if we use the measurement, then the slope of a line should be minus 2, which is already different from the 1, from m equal to 1. Now we know the slope. Let's now look at the intercept. And the intercept is defined as C equal to the mean of y minus the slope times the mean of x. The mean of y is 0.83 minus the slope is minus 2, and then the mean of x is 0.05, which gives us 0.83 plus 1. Our c is equal to 1.83. So our new line, yn, is minus 2x plus 1.83. So this is the line that we find based on the least square estimation. If we go back now to our previous plot, and then we want to plot yn equal to minus 2x plus 183, let's see now what we get. When x equal to 0, y equal to 183, and then when y equal to 0, x equal to plus 0 point something. So our line is actually supposed to be here with a slope of minus 2, which actually fits best the data because our data is also in that direction here. So, but then, how good do we fit our data? This is what we call goodness of fit. And for the goodness of fit, we can use the R square, which is defined in your book as 1 minus the sum of square error divided by the total sum, which is the yi minus the mean of the model square. We would like this number to be close to 1 to give us a very good fit of our data. If we now use the new line, which is y equal to minus 2x plus 183, let's see how good we can fit. Now, if we look at the response of y hat, let's call it n or yn, so we know it's our new line. 1x equal to 1, yn will be equal to minus 0.17. 1x equal to 0, which is our point that we had in the beginning. We will have our yn equal to 183, and then 1x equal to 0.5. We have our yn equal to 0.83. So what will be then the sum of square error? The sum of square error will be the difference between the true value and then the one that we have, such that for the first, if you remember our measurement, we have 3 points here, 0, 2, 0, 5 for the y. I will just repeat them here, 0, 2, 0, 5. So for the first one, we have 0 plus 0.17 squared plus 2 minus 0.3 squared plus 0.5 minus 0.83 squared, which will give us 0.667. This is the sum of square based on the measurement and the output, and we can also compute the total sum of square. Which will then be, as we saw here, each element minus the mean of the estimate. In this case, we call it total sum of square. We have then 2 minus 0.83. 0.83 is the mean value of our U plus 0.5 minus 3. So we have our measurement, and then we subtract the mean value of that, and then plus 0 minus 0.3 square, and this should give something in the range, in the range of 21667. We can then go back here and say, okay, now we know those two numbers. If we say 1 divided by 0.1667 and 21667, this will give us 0.92, which is very close to 1, indicating that our new line is a good fit. This is how we can do it by hand. Can we then check the solution using Matlab? So we just now to see if whatever we have computed by hand can be verified in Matlab. Also a way for you to learn how to use Matlab when you have more than 3 or 4 points, because then it becomes a bit complicated to do by hand. So let's define our points. The measurements were x1, x0, 0.5, and then our output were 0.2 and then 0.5. That's what we got from our experiment. Then how do you fit a line using Matlab? So you can say to Matlab, give me a line, I will call it my line, that fit x, y using a linear function, which is the polynomial of degree 1. And what we get, poof, is an error. Matlab says X must be a matrix with 1 or 2 columns. So the input that Matlab is expecting is a column vector. So what we do, how we do it, is then transposing our vector so that Matlab can accept it. We see here that Matlab has computed the slope as -2 and the intercept as 1.83, which is very close to our line that we got somewhere. So we have the slope here, -2, and we also had the intercept here, 1.83, and according to Matlab, we are very close with our handwritten solution. If you just ask for one output, MATLAB only gives you the coefficient of your line. And of course, if you want to fit it into a second order polynomial, then of course you can try that as well. But in this case, we are dealing with first order. Can we ask MATLAB how good is our fit? Yes, we can do that. If you want to ask MATLAB to do so, you tell MATLAB, okay, the first argument, the first output is my line, and then give me also a goodness of fit output. Then MATLAB gives you, first of all, your line, which is the P1x plus P2, the slope and the intercept, and then a structure of some of the error. So we have the sum of square error that we computed for 101667. Let me see if I can get it here. We have the sum of square error here as well. And then we can also have the R square. MATLAB is computed as 0.9231, that means 0.2. We also had the same value of R square as 0.92, which indicates a very good fit of our data. So this is an example to walk you through how to use those apparently complicated formula in real applications as well. And I will conclude the lecture here.